Let us take the hydrolysis of ester in the presence of acid into consideration. Let me give you the reaction first. See, this is ethyl acetate, ester. On hydrolysis, in the presence of acid, say HCl, gives acetic acid and ethyl alcohol. Okay. Now the interesting part of this is we are given any information about the ester, neither given any information about the acetic acid or ethyl alcohol. But interestingly, we are given information about the alkali, I mean the volume of alkali used up during titration with this reaction mixture at a different times. Okay, so the progress of this reaction is monitored by titrating the reaction mixture with the sodium hydroxide at a different time intervals. And in this titration, phenolphthalein is used as indicator. Let us see. Progress of this reaction is monitored using alkali. Let us take sodium hydroxide. Now, see, right at the beginning of the reaction, if suppose we titrate the reaction mixture with that of sodium hydroxide, that can be given as V0 or V0. Now, this actually gives us the volume of alkali, nothing but sodium hydroxide, used up at a time t is equal to 0. This can be given as directly proportional to, or simply let us give it as the volume of alkali used up exclusively for the acid that we are using. Because no, we did not get any acetic acid as of now. We are just about to start. We have not yet started the reaction. So we don't get acetic acid right at the beginning or right at the start of the reaction. So whatever alkali that is being used up is used only for HCl. Okay. Next. Consider Vt. This is nothing but the volume of alkali used up at a time t is equal to t. And similarly, V infinite. This is the volume of alkali used up at a time t is equal to infinite. Now, because we are continuing our titration, if suppose you consider this will of course include both the HCl as well as the acid formed. Isn't it? Even this also, I mean this at time t, and this of course at a time infinite. Okay, and this at a time infinite. Okay, let me give you the expression for k1, and that of course gives you maximum clarity. K1 can be given as 2.303 by t into log. See, if I want a, what I need to take is, see, because of course v infinite is what we need to take. But remember, v infinite is even including HCl. Of course, even Vt also. But that has to be subtracted, right? So just be little cautious. K1 is equal to 2.303 by T log A. What is A? Let us take V infinite minus, of course, V naught or V0, because this V0 is the volume of alkali used up exclusively for HCl. That has to be, of course, subtracted, because we want information about ethyl acetate or the ester, which on hydrolysis has actually given acetic acid. So we need to consider information pertaining to this acetic acid only, not pertaining to HCl. So that is what I am subtracting now. Hope you got my point. V infinite is both for HCl as well as this, because we are continuing the reaction. We have not stopped the reaction, and we have not taken sodium hydroxide every time freshly. We are just continuing to monitor the progress of the reaction. So in this case also, look at A. A can be given as V infinite minus V naught as usual. Minus, how about X? X can be given as, I mean, Vt is the volume of alkali used up at a time t is equal to T. That actually gives the amount of ester that has reacted. But that includes two things. One is HCl, the other one is acetic acid. So for that sake, let me actually take it this way. Even in that also would actually like to subtract V naught. Is that okay? So A is V infinite minus V naught. Every time subtract V naught, because that involves HCl. That okay? So final expression can be given as, how about this? This is V infinite minus V naught by V infinite minus, how about this? Vt. Okay. So that is how we can monitor the progress of the reaction. It is in fact V infinite by V infinite minus Vt only. But see, every time we are including even that used up for HCl, so that has to be subtracted. So every time it is minus V naught, V infinite minus V naught, even Vt minus V naught. So that finally gives us the required information. Now it is the optical rotation measurement, what is used for monitoring the progress of the reaction. Let us consider inversion of sucrose. We know that sucrose on hydrolysis in the presence of acid gives glucose and fructose. Now, let me say that sucrose is dextrorotatory. On hydrolysis, it gives glucose, which is again of dextrorotatory type, and the fructose, which is of levo or levorotatory type. But you know, the overall thing is levorotation of fructose is greater than that of the dextrorotation of glucose. So the overall thing is levo. Okay. See, you have started with a dextrorotatory one and ended up with a levorotatory one finally. So this is what we call inversion of sucrose. And the sucrose is of course called invert sugar. Now here in this case, this is what is taken into consideration to monitor the progress of the reaction. I mean, optical rotation is what we consider. Now suppose if we take the angle of rotation at a time t is equal to 0, this can be given as R0 or R0. Now angle of rotation at a time t is equal to t. See, angle of rotation at a time t or after a time t actually gives the concentration or the amount of sucrose that has undergone hydrolysis in a time t. Is that right? As a result of that, there will be some change in the angle of rotation. Of course, this at a time t, we can take it as t. And then angle of rotation at a time t is equal to infinite can be given as R infinite. Now, even here also you need to be little careful. If you want the amount of sucrose that has reacted during a time interval of t, then that has to be R0 minus RT. This can be given as directly proportional to the concentration of sucrose that has undergone hydrolysis in a time t. And how about this? R0 minus R infinite, because R0 is the beginning point, starting point. Now this actually gives us what amount of sucrose has totally undergone hydrolysis. Isn't it? Now come on. K1 is equal to 2.303 by T into log A by A minus X. Now this A can be written as what is A here? R infinite, no, R naught, because R naught is a positive value at extrarotatory one, R naught minus R infinite. Decreased, isn't it? R naught is maximum, R infinite is something less than R naught. So, because the angle of rotation is decreased during the course of hydrolysis. So, R naught minus R infinite. Now, again, this A is R naught minus R infinite minus, how about X? X is R naught minus RT, right? Now, this can be written as finally this is R naught minus R infinite by R naught minus R infinite. That is equal to, of course, the same R naught minus R infinite by, in the denominator, we get R naught anyway gets cancelled, right? So RT, a positive value, minus R infinite. Is that okay? Just like in the previous case, even here also, every time the R naught has to be taken into consideration because that is what you have actually started with. This is very interesting. Okay. Let us go for the methods of determining order of a reaction. We have about 5 methods to determine the order of a reaction. First one is initial rate method. Now consider a reaction AA plus a BB plus a CC gives rise to products. Now, suppose if you want the order with respect to A, you can find it out keeping the concentrations of B and the C as constant. Order of reaction with respect to A can be known, can be determined keeping the concentration of B and the concentration of C as constant. Okay. Now, let us take it this way. R naught is the initial rate, can be given as a directly proportional to A naught. I mean the initial concentration of A, I mean A 0 you can. Let this be with the power of A. Okay. Now, this is what we have to derive. Okay. We have kept the concentrations of B and C as constant so that the rate becomes independent of the concentration. Therefore, rate becomes independent of their concentration. Right? Now, this is the basic expression. Come on. Let us take two different initial rates and two different initial concentrations. R naught in the first case can be given as A naught in the first case to the power A. Let this be equation 1. Now, go for the second experiment. The second time, if R naught, initial rate at the second time is taken as R naught at 2, then that would be directly proportional to A naught at 2 to the power A. That's it. Taking 1 by 2. Equation 1 by 2 can be given as R naught 1 by R naught 2 is directly proportional to A naught 1 by A naught 2 to the power A. Right? Now, you know the order with respect to A can be calculated. Small a can be calculated taking logarithm. Let me write that. Log of, or else, no problem. Let me write one more. Log R naught 1 by R naught 2 is equal to A log A naught 1 by A naught 2. So from this, A can be calculated. Okay. What is that? See, from this, A can be given as log R naught 1 minus log R naught 2 by log A naught 1 minus log A naught 2. Is that okay? Now, A is order with respect to capital A. Small a is order with respect to capital A, which we have anyway determined. Now, the same way, even B and C are also determined. Okay. B, small b, and small c are also determined the same way by the same method. Okay. So this is initial rate method where we have taken the initial rate and the initial concentration. Okay. Now coming to the second method. Half-life method or fractional change method. Now, See, the relation between half-life and the initial concentration can be given as this. See here, T half is half-life, A is the initial concentration, and N is the order. Okay. Now let us take two different cases. I mean, two different half-lives at a two different initial concentration. T half 1 can be given as 1 by A1 to the power n minus 1. Similarly, T half in the second case can be given as directly proportional to A2 to the power n minus 1. Say this is equation number 1, this is equation number 2. Now from 1 and 2, or you can say 1 by 2. It can be written as T half 1 by T half 2 is equal to A2 by A1 to the power n minus 1, right? Now, what is the value of n? Nothing but the value of order of the reaction. See, straight away it can be given as, of course, this can be written as log T half 1 by T half 2 is equal to n minus 1 log A2 by A1. Now, after that, it can be written as n is equal to 1 plus this one log T half in the first case minus log T half in the second case by log A2 minus log A1. If you want, go for one more step here. Log T half in the first case by T half in the second case is equal to n minus 1 log A2 by A1. Right? Now that n is equal to 1 plus this one. So this is how order of the reaction with respect to that particular concentration term can be calculated based on half-life. Now it is Van 't Hoff differential method. Okay. See, in this case, it can be given as a minus a dc by dt, nothing but rate, isn't it? Is directly proportional to concentration of a particular species to the power n. So this is, of course, the rate in differential form. This, of course, is concentration. Now, taking two different things at C1, it is a C1 to the power n. Then minus a dc2 by dt is proportional to ct to the power n. This is equation number 1. This is equation number 2. Minus dc1 by dt by minus a dc2 by dt can be given as equal to C1 by C2 to the power n. Then taking log on both sides and writing the final expression for calculating the order of the reaction. Look at this. Log minus a dC1 by dt minus log minus a dC2 by dt by log C1 minus log C2. This way, taking the differential form and the concentrations at two different times, in two different cases, we can calculate the order. We can determine the order. Now, hit and trial method. Or is also known as integrated rate law method. Very simple. See, in this, we'll be substituting the given data in different rate constant expression right from the beginning, that is starting from the zeroth order. Zeroth order rate constant, and if a constant value is obtained, for the rate constant of a particular order, then it is confirmed as the order of the reaction. Just substitute the given information, given data. And if suppose you get a constant value for a particular rate constant, say K0 or K1 or K2 or K3, whatever gives you the constant value is final, is of course the order of that reaction. You can confirm that. Okay. Then the last one, that is Ostwald isolation method. See, in this, order of reaction with respect to a particular reactant is determined by taking the concentration of other reactants in large excess. Okay. Now, suppose if you got A, B, and C. First time, take B and C in large excess and determine the order with respect to A. by changing the concentration of A and finding the effect of change in the concentration of A on rate. Then go for B, then go for C, and finally sum of the powers gives you the order of the overall reaction. So these are the different methods used for determining the order of the reaction.